Hello friends, I welcome you all to this new series, and in this series we'll be learning that how to model mathematics in C++. Back few days I asked one of my students that whether he'll be able to write a program to find the differentiation or find the gradient of some function. So he said that he is not able to do it because that has not been taught to him. So I realized that once a person know programming, then he should be able to handle all sort of numerical computations as well. So to make the life easy for students, what I do now is I will be telling you that how to model or how to solve calculus, specifically few parts of it with the help of C++ programming. So without any further delay, let us start. Let's say I'm having a function x square plus 2x plus 3. I want to differentiate this function. So analytically, it is very simple task. So it should be 2x plus 2. Now, when it comes to programming, so you know that you have to deal with numbers there. So what should be done there, that you have to evaluate this at certain value of x, let's say 1.5 or whatever it is. So for that matter, you will be requiring numerical techniques, and that numerical technique is called as numerical differentiation. So in case of numerical differentiation, what we do is we reduce these differentials into difference equations, so which can be handled easily. Let's say I'm having this function and I'm interested in finding out the derivative of this function at this point x. So what we'll do is we will move slight right to this and at the same time slight left to this. That means we evaluate the value of function h unit on the left as well as h unit on the right. Slightly h is very small. Let's take that h is 0.0001. Now what we'll do is we will try to expand this function about these points. So fx plus h from the Taylor series, it is f prime x h plus f double prime x h square by 2 factorial plus f triple prime x h cube by 3 factorial and so on. Likewise for the point h unit on the left, that is f x minus f h plus f double prime x h square by 2 factorial minus f triple prime x h cube by 3 factorial and so on. Now friends, what you have done so far is the expansion. Now if you try to just uncover these or this, that means if you bring this onto one side, then on the right hand side you will be having from the first equation with certain other terms. And if you divide this equation, whole equation by h, then the highest order term will be of h, because h is a number which is lower than 1. So all the terms will be truncated. You are truncating them. So that's why this is of order h. Order of accuracy is h. Likewise, f for from here you will be getting fx minus h by h. Again, this will be of order h. Now, if you want these to be of higher order accurate, then you do what? You subtract these two equations. Once you subtract them, you will be getting 2h as the derivative. And now this time, as you are subtracting, so this will be getting cancelled out, this also will be getting cancelled out, and this term will remain. And if you divide it by 2h, so this will be h square accurate. So now the order of accuracy has improved. So this is called as forward difference, because you are moving to evaluate, you want what? You want the derivative of this function. To evaluate this derivative, you are moving in the forward direction. That's why it is called as forward difference. Whereas in this case, second case, you are moving in the backward direction. That's why it is called as backward difference. And here in this particular case, you are taking the values from left and right both, and then try to find out the value at the center. So that's why it is called as central difference. So this one is the central difference. Now this all is about first derivative, but if you want the second derivative, then what? So for second derivative, you do what? You add these two equations. So if you add this and this, what you will be getting? Fx plus h, then plus fx minus h, and on the right hand side this will get cancelled out and you will be getting fx, and then the twice f double prime x h square by 2 factorial, and then you will be having this h cube term will be cancelling out. So f 1 2 3 4 fourth derivative of this x, and then h to the power 4 by 4 factorial. Now if you segregate, and other terms will be there, and if you segregate this term, then you will be getting fx plus h. You bring this to left hand side, 2fx, and this term is also there, f, and then this is sorry, not 2, h square. So because this will get cancelled out, so the terms which are remaining are of h square divided by h to the power 4 will be of h square, because rest will be h to the power 4, h to the power 6, and so on. So the highest order term is of h square. So therefore this is again order of accuracy h square. So now you have this tool, and let us use this tool to find out the differentiation. Let us do what? Let us first try to solve this one, x square plus 2x plus 3. So now you are in the code blocks. First include the header file, then name space standard, so that you needn't have to write you needn't have to bring C out and C in every time in the scope. So now your main function, int main, and then return 0. Now first thing first, we will be writing the function. So as majority of the cases are only of floating point, so we will be using float. So let us say f is the function. Now if you look this closely, so f is the name of the function and it is taking this argument x. What is this as x? This can be integer, this can be float, but what we will be taking for generality as the float values. So we'll take this as float. Okay. Now one point of caution: if you want more accuracy, then you can take it as double. Okay. Now what is basically the function returning? It is returning x square plus 2x plus 3. So why not to take the advantage of math module? So hash include cmath. In case of C++, we use cmath. So return, and the function name is x square, that is power square plus 2 into x plus 3. I think this is the function. Okay. Now what has to be done? This function has to be called upon, and we have to evaluate these for first order derivative, f prime x from forward difference, backward difference, as well as central difference. So let us do it. So let us make some variable, that is df dx, using forward difference. I will be copying this, and this will also give you a glimpse that how order of accuracy works. Backward difference, and then the central difference. Okay. Now once this is known to you, then we have to find out what is the forward difference, what is the backward difference, and what is the central difference. So df dx forward difference is what? It is nothing but f x plus h, then minus f x, and then divided by h. And here in this expression, if you look closely, you are moving h unit ahead as well as h unit behind for backward difference. So in the program, you also require some h step size. So let us take that step size here itself as 0.001. The lesser the better. Okay. Okay, where it has gone now. The same thing we can do for the backward difference as well. So this is what? This is df dx forward difference. It should be df. Okay, this is the backward difference, and this is nothing but fx, then fx minus h by h. Now the question is where this function has to be evaluated. It has to be evaluated at some value of x. Let's say that value of x is 1. I am interested in 1. Now if you again move to the expression, the exact value when x is equal to 1, that is df dx when x is equal to 1 is nothing but 2 plus 2, that is 4. So our answers should come out as 4. Okay, so if you look this in the forward direction, we are trying to find out or predict the value of slope at this point from a point which is ahead of this point in the forward direction. So that is why this forward difference is biased toward the forward points. That means it should give values more than what was expected. Likewise for the backward. So as this is backward, so it should be biased toward backward point. So the output from the numerical output from the program should be lesser than that 4. And as the central scheme is taking both, so it should be close to 4. So let us see what happens. So here this is our forward backward. Now let us also write the central difference. So this is central difference. This is fx plus h and then divided by 2h. Once this has been done, you can print it. Okay. So C out and df dx and then the forward difference. This is forward difference what I have written. Okay. This is forward difference and let us write forward difference also. Forward difference and then we will be doing the same for backward difference. The variable, I hope I have written it correctly. Yeah, it is backward difference now. And then the central difference. This is CD. So if you run this program, this is saying I have missed this semicolon. And then again, now you can see that the forward difference is giving you a value 4.00114. Backward difference is giving you 3.9987 and the central difference is 3.999994. So from here you can very well appreciate the fact that all the formulas, whether it is forward, backward or central difference, they are giving you value, but the forward difference is biased towards the right, the backward difference is biased toward the left, whereas the central difference is very close to that value. And this is just because happening because of the order. The order of error in this case is of h. In this case again it is of h, whereas in central difference it is of order h square. So that's why it is happening. Okay. So friends, now you know how to find out the derivative of a single variable function. Okay. And you have already seen that the exact value should come out as 4. So what we'll do is in the next lecture, we will be evaluating the first derivative only of multivariable function and at different with respect to different variables. That means if a function is of x, y and z, then we will be evaluating the difference with respect to x, with respect to y and with respect to z. Okay, so in this lecture till this point only. Thank you very much for watching it.